Hi, this video will briefly cover the result in ring theory, commutative algebra, that if you have any ring that is unital and commutative, that is, if it is a ring with one and if the ring operation or multiplication is commutative, then it contains a maximal ideal. So we're familiar, hopefully, with ideals in rings. That will be like the basic supposition for using this video. So we'll just briefly go over what it means to be a maximal ideal specifically. So we state that some ideal that is closed under addition and scaling under the ring. So if you have x and y in M, then x plus y is also in M. And if you have, say, like little a, which is a scalar in our ring, then a times x for x in M is going to be contained in this. So it's closed under addition and scaling. And specifically, a maximal ideal is one that is not contained in any other ideal. So it is maximal, and we suppose that it is non-trivial, that is, it's not the entire ring. So it's properly contained in what we call A as our ring. And if you have any intermediate ideal here, then this statement implies that M equals A. So it is not contained in any other, or properly contained in any other ideal, right? So this is our idea of maximal ideal. And generally, to show maximality, it is a powerful tool to use Zorn's lemma. So Zorn's lemma is going to be what we're going to use now to show this result, and we will briefly go over it here. So it states that if you have a set S, which is non-empty first of all, and it's partially ordered, that is, if you can impose a relation which we call an order relation, and we might denote by less than or equal to, that satisfies these properties. So a partial order relation satisfies for every x in S, each element is less than or equal to itself, that is, it's reflexive. Then you have this comparability over here. So x is less than or equal to y is less than or equal to x implies equality. So x equals y for every pair of elements. And also, it has transitivity. So x is less than or equal to y and y is less than or equal to z implies that x is less than or equal to z in x, y, and z are all in S. So these are the axioms for a partial order relation on a set S. Now we'll look at a specific kind of a subset of these partially ordered sets, or posets as they might be called, which we'll denote by C, and they are called chains. So a chain is a subset if you have comparability for every pair of elements. That is, we notice that in a general partially ordered set, there's no supposition that if you're given two elements, you can say that one is less than or equal to another without loss of generality. But in a chain, you can do this, and that is the additional condition. So if you're given any pair of elements, you can either say, well, x is less than or equal to y, or y is less than or equal to x with respect to the order relation. So if every chain, now this is going to be the statement of Zorn's lemma itself, if every chain in our partially ordered set has an upper bound in the set, that is, if you're given, for all chains, you take for every element, let's say little t in C, you can find some x in S, so some element in our set, that bounds it above. So for every t, it is going to be less than or equal to, this should read x over here. So that is going to be the idea of bounding above. And if every chain has an upper bound, then we say that S contains a maximal element, right? This is exactly what we're going to use now in our proof to show that these kinds of rings have maximal ideals. And we want to think about, before jumping into it, what are we going to impose a partial order relation on? So we want to show maximality of an ideal, so we can take our partially ordered set to be, I'll start the proof here, and I would like to just write that as the video goes. Let A be, first of all, commutative unital ring. That's just our supposition. Then we can take all of our non-trivial ideals, that is, all the ideals except A itself, and we can put those into a set, which we will call sigma. So let sigma, be the set of all ideals which we'll say not equal to this ideal, where it's generated by 1 is just going to be the entire ring. So all of these properly contained ideals in A. And now, how do we impose an ordering on these? Well, natural idea, and what turns out we're going to use, is going to be inclusion. So we say that, let's say, if we have two ideals, one is less than or equal to the other if it is contained in it, right? So we order sigma by inclusion. Okay. Now, we have to, first of all, satisfy the requirement that the set which we're trying to show has a maximal element, in fact, is not vacuous. It's not empty. So there has to be at least some element in our sigma. And we know this to be true because we just have the zero ideal, because the zero ideal is, of course, always going to be in sigma for any ring, or at least any non-trivial ring. So we have sigma is non-empty because we have zero, element in sigma. Okay, now we want to get to our application of Zorn's lemma, really. So we have now this partially ordered set, and we want to take a chain in this. So a chain is going to look like a chain of ideals now. So let's say little a, so little a sub alpha be a chain of ideals in sigma, right? So it's going to be some sequence of ideals that are included in one another sequentially, and they're indexed by this alpha over here. So let it be a chain of ideals in sigma. Now, all we want to show is that every chain has an upper bound. So how are we going to formulate some upper bound here? Okay, so since this is partially ordered, first of all, and it is a chain, we have the fact that, let's say for all, or no, rather, if a sub alpha, a sub beta are both in this chain of ideals, so a sub are, let's say, ideals in the chain, so as to not repeat this notation of alpha. So remember what the idea of a chain is in the first place. It's that you have comparability for every pair of elements. So now given these two ideals, basically we can state, without loss of generality, or actually I'll put both cases, so a sub alpha is less than a sub beta, or we have a sub beta, which is going to be less than or equal to, or it's going to be contained in a sub alpha, right? Then we want to now form or postulate the existence of the maximal ideal. And to do this, for this chain or the upper bound, we can take, let's say little a, which is going to be the union across all these alpha, and we're going to take the union across all of these ideals here, right? Now the first thing we want to show, which is not immediately, it's not immediate, that this is going to be an ideal itself. So we have A to be an element in sigma itself. So to do this, how would we go about that, right? So we want to show, first of all, addition. It's closed under addition, and it is closed under scaling with respect to scalars in the ring. So A is an ideal, and we will just show that here. We take x, y to be in A. Then if it exists in this union, we can identify from this inclusion here that there are some ideals, let's say alpha and beta as we did here, such that x is in A alpha and y is in A beta, right? So x is in A alpha, y is in A beta for some alpha beta, right? Now we have from our chain condition here that one of them is included in the other. And without loss of generality, we will take, let's say, a sub alpha is contained. So without loss of generality, take a sub alpha, which is going to be contained in a sub beta, right? Now what we're going to do is just simply regard both elements as in the larger containing ideal, right? So if we have now that x is in a alpha, which is in a sub beta, we have x can be regarded as an element of a sub beta, as can y by supposition here. Then x is an element of a sub beta. X plus y is going to be contained in a sub beta. And it is an ideal. Hence, if we have x, y, a, implies that their sum, x plus y, is going to be an a, thanks to this chain condition here. Now we want to show scalar product, so let x be in our ring, and we want y to be, let's say, in our ideal. So y to be, or what we want to show to be an ideal, actually. So y, again, being in this union here, then there exists alpha such that y is in at least one of these ideals, right? So y is in a sub alpha, let's say. Then, so xy is, of course, now, by scaling and this being an ideal itself, we have this is going to also be an element of a sub alpha, simply viewing it as confined or localized to a sub alpha. So we have xy is in a sub alpha, which is going to mean that xy is in A. Great. So we've shown now that we have this union of all of these ideals in our chain, which is going to serve as our upper bound, because it bounds all of these ideals above, and it is itself an element in sigma. So this shows that A is in sigma, and it is an upper bound for our chain. And then we're just going to transfer to a slightly more general statement. Generally, if A sub alpha is a chain of ideals, then we have this union serves as an upper bound with respect to inclusion. And we are now ready to state our conclusion, because what we've shown is really all the machinery here, that every chain has a upper bound, which is going to be in our set that we want to show the existence of a maximal ideal in. So this exists in that, and we have, by Zorn's lemma, we have that sigma, which is going to be the set of all these ideals, must have a maximal element. Ideal, because in this case its elements are all ideals, right? And this concludes our proof. All right, so hopefully this was clear to follow, and thank you for watching.